This is a video about scientific notation. I'm going to be talking about what it is and why it's useful. I'll be talking about coefficients and powers of 10. This will include both positive and negative exponents. I'm going to be talking about proper formatting of scientific notation, and we'll be doing practice problems converting between scientific notation and what is called either decimal or standard format. This video and all of my videos have timestamps down in the comments that enable you to jump to one of these specific topics. So what is scientific notation and why is it important? I want to talk about the contents of this jar. This jar contains 58.4452 grams of sodium chloride. Sodium chloride is table salt. When you add salt to your food, you are adding sodium chloride. And this quantity can also be called 1 mole. Mole is a certain quantity. The way that the word dozen means 12, a mole is specifically a quantity of a very huge number. I'm going to be writing that number on the board in addition to the mass of 1 sodium plus 1 chloride ion. So this jar contains 1 mole of sodium chloride. That means that this enormous number is the number of sodium ions in the jar, and we have this same number of chloride ions in this jar. When our brains look at this number, we can't really comprehend it. We just see a huge, huge number. Because sodium and chloride ions are so tiny, because there are so many of them in this small jar, if we look at the mass of just 1 sodium ion plus the mass of 1 chloride ion, we have a tiny number. Notice the decimal point at the beginning, then lots and lots of zeros before we get to the 9705 grams. Human brains are really, really great at understanding numbers from maybe 1 through 20. But when we see huge numbers and tiny numbers, no one really comprehends them. If you had $1 versus $1 million, there is a huge difference. But if I take 6 zeros off the end of this, you're still just going to look at this and see an enormous number. These are numbers that we can't wrap our heads around. So this is why scientific notation is important. Scientific notation is a way of writing numbers that's just easier for our brains to understand. So I'm going to rewrite both of these numbers in scientific notation. Okay, so for our first number, I wrote 6.022 times 10 to the 23rd power. For the second number, for our tiny number, I wrote 9.705 times 10 to the minus 23rd power. Units are the same, grams. So, scientific notation has 2 parts. We have a coefficient at the beginning, and then we are multiplying by some power of 10. Let's first look at this coefficient at the beginning. What you need to do is move the decimal point to immediately after the very first non-zero number. Now this number, I did not actually write a decimal point at the end. Whenever you don't see a decimal point, we just assume it's at the end. But let's move the decimal point to immediately after the first non-zero digit. Our first non-zero digit is this 6. So I am moving the decimal point to immediately after it, 6.022. And I am not bothering to write all of these zeros at the end. Then this times 10 to the 23rd power, this is telling us that we moved the decimal point 23 places. So let's start from where it originally was at the end and count how many places the decimal point needs to move to be put immediately after this 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So this is 23. The reason that this is a positive 23 and not a negative 23 is that this is a huge, huge number. The positive versus negative is telling us which direction the decimal point needed to be moved in. So positive exponents are always large numbers. So this is a large number. We needed to move the decimal point to the left in order to convert it into scientific notation. Now let's look at this second example, our tiny number. We figured out the coefficient the same way. We moved the decimal point to immediately after the first non-zero number. So we have a 0 point, lots and lots of zeros. Just keep looking through them until you get to a non-zero number. This 9 is our first non-zero number. So we have 9705 at the end. I am moving the decimal point to immediately after this 9, 9.705. The times 10 to the minus 23 is telling us how many places we move the decimal and in what direction. So let's count. If our original decimal point location is here and we need to move it to immediately after the 9, how many places is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So that is why this is a 23. The reason it's a negative is that this is a very, very small number. You had to move the decimal point to the right to convert from the original number into scientific notation. So scientific notation is useful for a few different reasons. First off, I mentioned that the human brain is good at understanding numbers from about 1 through 20. We put the understandable part of the number at the beginning, 6.022 versus 9.705. If you are always putting the decimal point immediately after the first non-zero number, you're always going to end up with a number from 1 to just less than 10, 1 to 9 point something. And this exponent is just telling us large positive exponent is a huge number, large negative exponent is a tiny number. We are separating the understandable and not understandable parts of the number. Also, it's just a lot faster to write these numbers. If you are looking at this in standard format, also called decimal format, and you're trying to comprehend this number, you would probably need to count how many zeros there are at the end anyway. This is just putting that all in one place. I can say the same thing down here. This is an overwhelming number of zeros at the beginning. In order to comprehend this number, you would need to sit here and count them. We are just saying how many places we needed to move the decimal point. Let's talk about the different parts of the number of scientific notation. So this number at the beginning, this is called the coefficient. The coefficient is a number from 1 to less than 10, and it's going to be written at the beginning in scientific notation. What I mean by from 1 to less than 10 is we want a one-digit number at the beginning that's not 0. So I mean, the lowest it can be would be 1, the highest it could be would be 9.9 repeating. But the coefficient is this number at the beginning. The second part of scientific notation is times 10 to some power. So we're going to be looking at this in a little bit more detail, but we need to multiply by some power of 10. Let's talk about powers of 10 in a little bit more detail. Let's talk about these powers of 10. So you can think of scientific notation as a math problem. The coefficient, the number at the beginning, happens to be formatted in a certain way, but we are then multiplying that by some power of 10. Let's look at this first example, 10 to the power of 3. What this means is I take our base number, which in this case is 10, and I multiply it by itself 3 times. In other words, 10 to the power of 3 equals 10 times 10 times 10. This is also equal to 1,000. Notice we have 10 to the power of 3, and it is equal to a 1 followed by 3 zeros. That trend is going to continue. So when we have 10 to the power of 2, this is going to be equal to 10 times 10. We need to take the base number 10, multiply it by itself 2 times. 10 times 10 is equal to 100. Notice we have a 1 followed by 2 zeros. 10 to the power of 1. We need to take 10, multiply it by itself 1 time. In other words, we don't need to do anything to it. This is just equal to 10. But the trend is continuing. 10 to the power of 1 is a 1 followed by 1 zero. Now, 10 to the 0 power. This might be a bit trickier, but the rule in math is that anything to the power of 0 is always equal to 1. So this is equal to 1. But our trend is continuing. 10 to the 0 power, we have a 1 followed by 0 zeros. Now, negative exponents. Think of these as dividing by 10 to the first power. So 10 to the minus 1, this can be thought of as being equal to 1 divided by 10 to the positive 1. In other words, 1 divided by 10 is going to be 0.1. But look at our decimal point location over on this column so far. The trend is continuing. Each time, decimal point is moving 1 place to the left. That is continuing when we get into negative exponents. But 10 to the minus 2 power, this is going to be equal to 1 divided by 10 to the positive 2 power. In other words, equal to 1 divided by 100. So as a decimal, this is 0.01. Again, we move the decimal point 1 more place to the left. This trend is going to continue indefinitely. So 10 to the minus third, we can say that this is equal to 1 divided by 10 to the positive third. This is equal to 1 divided by 1,000. But we are once again going to move the decimal point 1 more place to the left. 0.001. So think of scientific notation as if it is a math problem. We are literally multiplying the coefficient by some power of 10. And what this power of 10 is doing is telling us how many places and in what direction the decimal point needs to be moved. So let's talk a bit about proper formatting of scientific notation. Let's look at these two values. 1.02 times 10 to the third and 10.2 times 10 to the second. If you were to treat both of these as math problems, you would get the same answer for both of them, 1020. However, if you are asked which one of these is written in proper scientific notation, it's only going to be that first one. This second one is not in scientific notation. So our coefficient, our number at the beginning, needs to be from 1 to less than 10. What that means is a number from 1 through 9, which may or may not be followed by digits after a decimal point. But this is too large of a number. Writing this properly in scientific notation, we can only have one non-zero digit before a decimal point. Let's do some practice problems in which we convert these 4 values that are in scientific notation into decimal format. So problem A, 1.487 times 10 to the third. You can treat all of these as if they are math problems. So I'm going to rewrite this. as 1.487 times 1,000. 10 to the third is a 1 followed by 3 zeros. What I need to do to convert this into decimal format is move the decimal point 3 places to the right. 1,487. So problem B, 2.6 times 10 to the minus 2. We have a negative exponent. Once again, you can treat all of these as if they are math problems, but a negative exponent means you need to move your decimal point to the left. So I'm going to rewrite this as 2.6 times 0.01. If you have 10 to the minus 2 power, that is 0.01. But you would need to move this decimal point 2 places to the left. 0.026. This is my decimal format. Problem C, 9.7 times 10 to the 6th. We are going to need to move the decimal point 6 places to the right. So it was after the 9, and we moved it 6 places to the right. 1, 2, 3, 4, 5, 6. So 9,700,000. Problem D, 8.3 times 10 to the minus 5th. We are going to need to move the decimal point 5 places to the left. 0.000083. So the decimal point was originally after the 8, moving it 5 places to the left. 1, 2, 3, 4, 5. So in the case of all of these, if the exponent was positive, we were moving our decimal place to the right. If the exponent was negative, we were moving our decimal place to the left. Now let's do some practice problems where we have numbers in decimal format and we want to convert them into scientific notation. So for all of these, we are going to need to figure out what our coefficient is. You want your decimal point in the coefficient to be immediately after the first non-zero number. So for problem A, 1,327. For your coefficient, put the decimal point immediately after the 1, 1.327. We then need to figure out what power of 10 we would need to multiply this by. So times 10 to some power. How many places do I need to move this decimal point by in the coefficient to get 1,327? I need to move it 3 places. And it's moving to the right, so that is a positive 3. So 10 to the positive 3 power. To double check your work, you can take this scientific notation answer and treat it as a math problem. You should get your 1,327 back. For our second problem, B, 0.003, the coefficient would need to have a decimal point immediately after the first non-zero number. First non-zero number is this 3. It is also our only number in the coefficient. 3 times 10 to some power. So to take 3 and convert it into 0.003, how many places do I need to move the decimal point by? So if my decimal point were after this 3, 1, 2, 3, I would need to move it 3 places to the left. So this is going to be a 10 to the minus 3. Problem C, 9,600,000,000. Okay, coefficient is going to be 9.6. Decimal point has to be immediately after our first non-zero number. Times 10 to some power. If my decimal point were after this 9, how many places would I need to move it by to get it to the end? 1, 2, 3, 4, 5, 6, 7, 8, 9. This is times 10 to the 9th power, 9.6 times 10 to the 9th. This is a large number, so that is a positive exponent. Problem D, 0.0000087. My coefficient is going to be 8.7. I would want a decimal point immediately after my first non-zero number. And I need to take this times 10 to some power. So how many places and in what direction do I need to move the decimal point by if it were after the 8 to get it into this place? 1, 2, 3, 4, 5, 6. This is going to be 10 to the minus 6th power. 8.7 times 10 to the minus 6th. So if it is a very small number with a lot of leading zeros, it is a negative exponent. If it is a large number, it is a positive exponent. In every single one of these cases, you can treat your answer in scientific notation as if it were a math problem. You should get back your number in decimal format. Thanks for watching Chemistry in a Nutshell. If you feel that I've earned it, please like this video and subscribe to my channel.